to be talking a little bit about our journey building a logs product at Netflix to serve centralized logs. I'm Daniel Muino. I've been at Netflix for a really long time, over 14 and a half years. So I was here, I was actually hired by Yuri Israelevsky, who is a co-founder and president of ClickHouse. So full circle. And basically, the problem is quite simple, right? We need to ingest petabytes of data every day for operational logs, several petabytes. We need to have relatively fast queries. And it needs to be relatively cheap, right? So we don't want to spend too much money. So it sounds simple. But for the longest time, Netflix did not have any kind of centralized log. So roughly around, I think, 2020, some teams basically were SSHing into the instances, grabbing some logs. Logs were rotated and uploaded to S3, so they built some tools to download logs from S3, run grep in parallel across the logs. Wasn't ideal. More enterprising teams created some Elasticsearch, typical Elasticsearch setups, where they use Elasticsearch, Logstash, Kibana. Awesome. And basically, that worked, but the first time they had to do an Elasticsearch migration from one version to the next, or had to maintain the Elasticsearch clusters, or have to debug problems of missing logs in the pipeline. They were not happy because our engineers are mostly focused on building applications, adding features, improving the recommendation system, things like that. They don't want to be dealing with operational issues. So since Elasticsearch worked for these few teams, there was somewhat of a push to have something like that available and maintained by a central team. So that's a little bit of the prehistory when we try to use Elasticsearch as the foundation of the centralized logging solution. And it worked relatively well. We needed to procure an Elasticsearch cluster for each team that wanted to onboard. Some minor configuration changes where you say, these are the log files that you want to upload to the Elasticsearch cluster. This is where the timestamp field lives. This is the message field, things like that. So there were some manual steps, and it was incredibly fast. I mean, doing very complex queries were taking a few hundred milliseconds at worst. So it was really, really good, but really, really expensive. We only onboarded like 20 teams, 20 applications. We call them microservices and applications. I'm going to be using those words interchangeably. But it was very expensive. So we did like 20. We extrapolated how much it would cost to do somewhat around 8,000 that we have. And it was just prohibitively expensive. It was just laughably expensive, and basically that's what the management told us. So we started from scratch. At the same time, 2020, we had been using Iceberg, which was as you're all very familiar with, a table format that was developed at Netflix and then donated to the Apache Foundation. And we were using Iceberg in certain cases for metrics, in particular for me. So we decided, let's try to use Iceberg. It should be much cheaper. We can just write some Parquet files to S3. We can add them to some Iceberg tables. And we can use Presto at the time, Trino now, to query those Iceberg tables. So we tried that. We did some proof of concepts, see if it was feasible, what performance we were getting, because if you have a lot of data, then it can become very slow. And as long as you created the Parquet files of the right size, if we had some processes to basically route the data in a way that allowed us to create these, let's say, 128 megabyte size Parquet files or so, queries were reasonable. So instead of taking, let's say, 200 milliseconds in Elasticsearch, it was taking, let's say, 2 to 5 seconds. But when we run the numbers to see how much it would cost to do all of the Netflix streaming apps, it was between 250 and 300 times cheaper. So that's what we did, right? I mean, if you are told instead you have to wait 2 seconds for a query, but it's significantly cheaper, then yeah, that's what you have to do. And the one problem is because you have to create these files of the right size, you need to buffer at several stages in the pipeline until you have the right data. And one way we achieve isolation across the different applications is we created an iceberg table for each of those applications. And if the application requires a different retention, it's just a property in the table. And the beauty of this setup was that we have a central team at Netflix that owns Iceberg, the Iceberg catalog. It owns the Trino clusters. So we, working on the login side of things, didn't have to do any of that maintenance. It was just provided for us. They own the S3 buckets. They work with AWS to have really high partitioning of that bucket. So we didn't see throttling of S3 calls and things like that. So that was basically the first version of what we call inside logs, which was, this is a very high level, but more or less, we have different services that are sending logs through an agent. And using HTTP, they send messages to this ingester, which is a set of nodes that buffer data for a few seconds, writes the data to S3, and then the transformer basically reads from S3. We use kinesis just to say there's a new file in S3, and then we checkpoint once we have processed the file. So in case there are catastrophic failures, we can retry from the last checkpoint. So we normalize the data in the transformer. We generate some basic analytics, like certain counters for the different log types. And then, because we need to do commits for a particular table, we have to put another message in the kinesis queue and add those things that are later processed by this committer, which is just committing these Parquet files as it reads them from the queue. This is sharded by the application at that point. So basically, a single node will process all the files for a given application. The main problem is this committer needs to wait until it has enough data to commit relatively large files. So we wait until we reach a certain size or certain time has elapsed. And then we commit into Iceberg. And we use Trino or Presto at the time to query those Iceberg tables. So basically, the main issue is that when we created this product, we had a 5-minute SLA. And it was taking between 3 and 5 minutes for the time a log was produced until a log was available for search results. So that's not ideal. And the other problem were the query latency for very simple queries. I mean, it's reasonable. So this is the first version. That's when I joined the team. The main problem we had at the time was one of the main responsibilities of the transformer is when it normalizes the data, it assigns a unique identifier. So similar log messages get the same unique identifier, even if they are different, but they look the same to a human. So the classical clustering problem that you find in any intro to machine learning. So we try to use machine learning. We run into so many problems with that. I can talk about that after if you want to get the details, but it was prohibitively expensive. It was very slow, and it was unreliable, mainly because the libraries for machine learning are mostly written in C++, and we're a JVM shop. So using JNA and out-of-heap memory caused many, many problems. In any case, we created something that works. It's not ideal, it works. So we launched. This is the V1 version. And people started using it. We onboarded applications. We worked with different platform teams. So instead of having to configure the collectors to say, these are the files, this is the format, we provided them an SDK. So the SDK sent JSON lines to our agent, so there was zero configuration required for applications. It just worked. As long as you're on the path using either Java or Node.js or Python, things just worked. So that's first version. The problem is, okay, we finally have centralized logs. But it's a little bit annoying to use. Every time you make a tiny change, it takes 3 to 5 seconds for the page to refresh, and you're trying to troubleshoot a particular problem. I mean, at the time, we didn't come to ClickHouse very early. This is 2021. So there was already a lot of buzz about ClickHouse being able to handle very large data sets very efficiently. So we tried it. But first, okay, so, I mean, you usually hear these stories, but you actually look at the code and you are very skeptical that those stories are true, right? Something weird. But we look at the ClickHouse code. It was really, really good, clean C++ code. We look at the overall design. It made sense why it would actually work. So we tried it, but only for a subset of data. We only tried it for errors and warnings. Worked. Query latency is really fast. Okay, let's try it for all logs. And it worked. I mean, we had to do some work in many cases, to work on the ingestion side, some changes, but for the most part, it worked. And the beauty of it was that ClickHouse had many tools that allowed us to just dump logs into it. We used, at the time, buffer tables. We since switched that. But those buffer tables were doing the work that we were having to do manually, like buffer log events in memory until you have enough data to dump it. And we didn't have to shard by app. We could just write the data, and we just set the primary key in the ClickHouse table saying, this is the primary key. The application is your primary key. And then we have a partition by the hour of the datetime. And that's it. It just worked. I mean, we didn't have to do much. So next step, let's replace. Let's have this grand vision of replacing Iceberg completely. We are no longer going to be using Trino. We also use Druid for analytics, where we can just use like some merge tree tables for getting the aggregates in ClickHouse. So we tried, and the problem then became the operational aspect. It's not trivial to operate once you have a lot of state on each individual node. I guess this is one of the main reasons why ClickHouse Cloud is so popular. You completely ignore all of the things that you need to do to have a, let's say, a node that has 6 months of history. How do you, because once you have a lot of history on a single node, you need to start worrying about backups and restores. The way we were doing backups, for example, was to upload the files to a particular S3 bucket and a prefix. Let's say we have a 100-node cluster. We assign a slot to each of the nodes. Let's say node 3 dies. The new node that replaces that node in the cluster gets a slot assigned, which will be slot 3. So that downloads from the 3 prefix in the bucket. But what do you do when you need to resize the cluster? You go from 100 nodes to 120 nodes. I mean, that doesn't work. So we had to spend a lot of time just working on those operational problems. But the setup is much simpler, right? So basically, you just get the logs. You can ignore the streaming side, and they just dump it into something that will be right into ClickHouse. And it was the latency. Worst case, we were getting like 2-second query latencies, but usually it was like in the 500 millisecond range. It was absurdly fast because it had to scan so much data that to me, I think it was impossible the first time I saw it, but I mean, it worked. So the main problems that we had with ClickHouse, okay, as I mentioned, the stateful nodes, right? You need to have like a backup and restore strategy. If you use replicas, at the time we were using Zookeeper provided by a central team. Then because of performance reasons, we switched to ClickHouse Keeper, which has much faster basically latencies for all of the ClickHouse operations. But maintaining ClickHouse Keeper is not easy. Like if you need to do an upgrade of ClickHouse Keeper, You need to be worrying that you don't take all the nodes down because you lose quorum, that if you somehow ClickHouse Keeper goes down for more than a few seconds, ClickHouse server gets extremely unhappy. And basically, we need to start from scratch. We need to drop all the history we had and start from a new, fresh deployment. And then the other problem was how to deal with the expensive queries. ClickHouse provides a plethora of options on how to do resource allocation to users using quotas, like this user can run up to n queries during this time period. You can set for a given query, this is the max number of rows to scan, the max number of bytes that you can use, the maximum memory. You can even set the OS thread priority. The problem is how do you get the right values for those queries so that an abusive query gets terminated early, but a normal query that might need to scan a bit of data doesn't. So how do we protect the cluster, but also provide some reliability? So what we ended up doing is using ClickHouse for recent data. The vast majority of our queries are for the last hour, last 3 hours, last 6 hours. So if we have a day of data on ClickHouse, we can answer all the queries very quickly, and then we can use Iceberg for the rest. Let's say our security team needs to run a scan of all the data in the table, looking for particular PII that was logged by accident. They can do that with Iceberg. We don't have to worry about we're terminating that query because it's scanning too much data. So basically, that's what we ended up doing. And this is an actual architecture. I just copied this from our internal docs. So I'm not going to go into this, but I can talk about it later if you're interested. But basically, we write to both. If we have problems with ClickHouse, we send the queries to Iceberg. We haven't had any kind of problems lately, luckily. But this is just in case. I don't know, I'm out of time, but I was hoping I could do like a live demo to see the abusive queries that we are actually sending to ClickHouse. I don't know if you're interested. I can do a quick, like a couple of minutes. And sure. So we have two UIs here. This is our old UI. This is our stable UI. We are scanning here a lot of data. I'm going to refresh this just to see the main thing. If we look at the time, it's 6:40 p.m., and you can see the time of the freshest log message. It's 6:40, right? So we are usually in the 15 to 20 second latency for data freshness. And then we can do, let's say, these look like access log. I want to, let's say, exclude this from the result. And then here we can see a histogram. This is grouping by level. We can say, so we need to actually do the counts and do the group bys. Oh, sorry. So let's say we look for a particular substring. This is looking, sorry. The actual message. Something like this. So this is looking like a substring contained, so there's no way ClickHouse can use any kind of optimization here. It has to scan the data, and it gives you the results pretty much immediately. Like this is a few hundred milliseconds at worst. And we can generate the histogram at top there with the, those are basically just the counts. So if we look at the, hopefully I can share the, actually no, I want to go to the new UI that is being built. This is actually much better. Here, I want to exclude those loggers for those access logs. That's very good. You can see that we are very quickly getting all the different values for the logger tag and getting a count. Let's say I don't want to, that particular access log. And you can see it's immediate, right? This used to take so much time. You weren't able to do this, trying to find the needle in the haystack quickly. Here, we are getting the most frequently occurring values. Here, we're just looking at the level, so there aren't that many. But let's say I look at the fingerprint hash, which is this unique value. And you can see we need to get, across the whole time window, these are the top occurring fingerprint hashes, in this case. and their counts. And I want to count also how many we have that are not included in the top K. And I want to bucket those by time. And the query is pretty much immediate. And if you look at a particular event, we can see here the full JSON event. And just because one day I was bored, I added a feature because things that are not in the schema, you were not able to project them. You could only look at them here. So I added a feature where you can just use JSON path to extract anything from within the JSON blob for presentation purposes. I was horrified when I saw that the new UI says, you can use this as part of the query. And it basically has to scan a really large string blob. It's not a JSON column. It's a string blob. It has to parse it as JSON. It has to extract within the JSON a particular path, and it has to perform a very complex query across the time, and it's taking milliseconds. So the ability to be able to experiment, like let's say I want to add even more, like let's say another condition. I want to say the formatted message contains. And they are provided even auto-completion on something ridiculous. So I don't like this, the fact that they are doing this, but I don't know. Right? Let's say this is just a string. And we are able to get those interactive features and this is something that's been built, so you will see some issues. It's alpha. But the fact that you can experiment and try to see if new features work for users, if they are actually useful, is really, really convenient, and it's pretty much magic. So I just want to thank you to the ClickHouse team, and that's about it. If you have any questions, I'll be more than happy to answer them, but since I ran out of time, maybe we can do it during the meetup.